Good morning, everybody. Welcome to this edition of Kundinger Presents. I'm Paul Kundinger, president of Kundinger Inc., and I'll be your host today. We're excited to be presenting the Parker Electromechanical Industrial Linear Actuators today. Part of our excitement is Kundinger recently added on the Parker Electromechanical full line of products and look forward to being able to offer the products and solutions to our customers and continue to add value to the existing products and solutions we provide today. So this is kind of our initial kickoff of some of the products that we are going to be offering going forward, and look forward to sharing with you today, and have invited Andy Thomas from Parker's Electromechanical division, an account manager, to help share some important information around the linear actuator line with Parker. We are using the chat feature today for any questions. So if you have any questions during the presentation, just launch those into the chat and we'll be monitoring that and ask those as time permits. And at the end of the session, if you have any further questions, you can use the contact information that you see on the screen right now and send an email to either myself or Adam, and we'll be glad to answer those. In your control panel, you'll also see that there's a materials section, and we've added some different materials for you to download, whether it be some PDF files that relate to the topic we're covering today, or just some general information for the Parker Electromechanical line itself. So those are yours to download. And again, if you have any questions along the way, feel free to put those in the chat and we'll answer them as we can. With that, I'm going to turn it over to Adam.
My apologies. I couldn't hear what you said.
Let me unmute Adam here. There we go.
All righty, thank you, Paul. As Paul mentioned, I'm Adam Thomas. I'm an account manager with Parker Hannifin. I focus on industrial OEMs and some overall product type stuff with the industrial lines. So we're going to get right into this. We do have a good bit of material to get through today. So we'll start off with just giving an overview of what we define an electromechanical linear actuator to be. We'll get into some specifications, really what kind of numbers and data do you need to select one of these systems properly. Then we'll go through some product design features on a few of our sort of target product lines and go through those products as a whole. So if we start from the basics, what do we define as a electromechanical linear actuator? So we call this a packaged product combining linear guidance and drivetrain technologies that are going to convert electrical energy into linear mechanical motion. So you have your guidance elements that are actually supporting the payload, your drivetrain that is actually moving the payload back and forth, and then some sort of motor to make everything move. So when we say industrial, what are we really talking about? Well, we refer to industrial as more of a market segment, not necessarily an application type. Typically, we'll say repeatability is less than 50 micron. We'll consider those to be industrial. When you start getting on to the micron and sub-micron type level, that's when we're going to start calling things more of a precision type application. We kind of classify motion applications into three basic types. We'll have make, measure, and move. Make sort of refers to the actuators performing some sort of manufacturing operation. And this is kind of a gray area between precision and industrial, just because of really what kind of accuracy requirements do your systems require. So if we're talking, high forces for things like pressing, tool forces from cutting in machine tools, or precision if we're looking at machining something, you need your parts to come out within tolerance. And then any kind of sort of like a medical type manufacturing where we may be taking blood samples and manufacturing like vaccines or things like that. Obviously, we're down on the sub-micron type level just due to the size of those sort of things. What do we care about in make? Obviously, accuracy, things coming out within tolerance, and speed. In any type of automation, higher throughput means less time running the machine, higher capacities, reduced cycle costs. Measure applications are typically going to be precision. These are your CMMs, your inspection type machines. Every other specification other than accuracy really seems to come second in these sort of applications. And move is typically going to be what we would classify as an industrial type, just because even if it is in some sort of medical type device, moving is really a necessary evil in any process. It really does nothing but add cycle time. Really, you're adding cost, not necessarily value. So the primary goal in these cases is speed. Some cases this can be precision if you're just moving medical samples around or moving pipetting type applications. Some of those well plates can get pretty small, but typically in packaging and material handling, we're going to refer to these as industrial and specify them as such. So we start talking about performance, we really need to figure out what kind of specifications we need, what sort of numbers do we need to specify these products and select them correctly. And these are all sort of specifications that you'll see in any kind of catalog for any kind of actuator. So just go down through the list. Maximum speed. So this is going to be limited by your drivetrain and your guidance. So in a screw-driven actuator, if you start spinning the screw too fast, it turns into a jump rope. Linear bearings and belt drives end up being your limiting factor. But by this, we just mean how quickly can I move the payload back and forth and measured at something like meters per second, feet per second, things like that. Maximum acceleration, very important for determining what kind of move can we actually get to. If, say, you need to go 6 meters a second, but you only have a 1 meter long actuator, your maximum acceleration may mean that you're never actually able to get to that true 6 meters a second. These are going to be limited by, again, your screw and your linear bearings, rolling elements kind of turn into skidding elements if max accelerations get too high. Thrust forces, really how much force can the drivetrain apply to the payload? So how much force can I use to push things forward or backwards? Determined by acceleration, friction, and horizontal and vertical applications. You're obviously going to be coming up against gravity as well. But payload acceleration and friction typically end up being determining what our thrust forces would need to be, or if we need to apply some sort of pressing force as well. Normal load. So this, you'll see normal load specs in everyone's catalogs. I always say these numbers are really for nothing else than bragging. There's a lot of specsmanship that go into these kind of numbers. You might see an actuator that you can put 2-3 tons of mass on, but you're not able to actually put any kind of offset loads on it, and your thrust forces on the actuator mean that you're only able to accelerate that thing at a fraction of a G. Moment loads are really what really determine how much you can put on an actuator. So if you have a payload off to the side, even up off of the carriage in the vertical direction, because there's no such thing as a zero height type payload, you'll have both static and dynamic moments. So static just meaning it's there just due to gravity or just the way the payload is mounted, but dynamic comes into effect into cases due to acceleration. So if I have a payload sitting a couple inches up off the top of the carriage, I go to accelerate, I am putting, my contact point is above the carriage, I am putting a moment load on that carriage. Repeatability. So what is our error band when returning to the same point? So if I command a 5 millimeter move and I'm going to do that over and over and over again, how repeatable, what is the error band when I return to that same point over and over again? Do I get to that same point within 5 micron, 10 micron, 20 micron? If that amount of error is low, the unit is said to be repeatable. So stroke, this is obviously something that your application is going to determine. How much travel do you actually need? The maximum stroke of an actuator is going to be dependent on, typically the drivetrain elements are going to be your limiting factor. You can only make ball screws so long before they just start sagging and turning into a frown under their own weight. Belts, the same sort of thing, but obviously typically you can get a belt actuator much longer than you can get a screw actuator. IP rating, this is very, very important in a lot of industrial applications just due to what kind of environment you're in. Do you have coolant splashing? Do you have chips from a machining type process? Dictated by the environment. So these are rated by 2 numbers. So the first number, and we use the example of IP54, The first number is your ingress rating against solids, and the second number denotes protection against liquids. So IP54 meaning protected from limited dust ingress. So if you have fine dust in your environment, protected from that for the most part. And the 4 meaning protected from water spray in any direction, not wash down though. Think more of like splashing in that case. Cross-sectional inertia. This is a pretty important one depending on how you're mounting these units. If you're mounting a unit down to a flat plate, you don't necessarily care about cross-sectional inertia. But if you need to mount a unit in a unsupported type fashion or a self-supporting fashion, say you're just putting legs on the end, you're going to need to know how rigid the actuator is and how much deflection you're going to get. 2 reasons we care about deflection. 1, eventually we'll start binding up the bearings inside the actuator and the actuator is not going to move. And 2, how much deflection can you tolerate in your process? High stiffness adds cost and weight. It also takes up a good bit of space as well. So if you don't need it, typically something you'll want to stay away from. And life. So this is where we sort of differ. You'll see through the Parker catalog, we make rotted cylinder type products. This is where the big differentiator comes between us and a hydraulic type cylinder. Mechanical drivetrains are wear components. There's really nothing we can do to get around that. They're all bearings. We have life calculations to go along with them. But I know people always typically say they want their actuator to last as long as possible, but setting realistic expectations is important with these sort of things. We can calculate based on your forces, your speeds, what the life of the actuator is going to be. And understanding your duty cycle is important as well. So we have all of the specifications in our catalog from a max perspective will get you about 2,540 kilometers of life. How much that is in your application depends on your speeds and your duty cycles. But it's always important for us to sort of do the math and see what 2540 actually means in your application. And sometimes you'll be surprised how long that can actually get you. And in some applications, that's nowhere near enough. So we need to start looking at going under what catalog ratings can say. So let's talk for a second about Specsmanship. It's very difficult to just size something out of someone's catalog because you don't really know what kind of marketing fluff has gone into their specification numbers. So I'll give an example. We'll talk about a product later in the presentation called the HMR24. That unit is capable of holding about 3 tons of mass, and it's also capable of 5 Gs of acceleration. Now, does that necessarily mean I can accelerate 3 tons at 5 Gs? Not necessarily. Typically, what sort of choice you make in one specification will dictate your options with another. For example, astronauts experience about 3 Gs during a rocket launch. So kind of put in perspective what 5 Gs actually means. That would be an insane amount of force for any kind of mechanical drivetrain to react. So typically the way we combat Specsmanship is with a product that I can go into, or a tool I can go into a little later if we have time, called Virtual Engineer, basically where that's a web-based sizing tool where you'll be able to type in all of your application details, tell us exactly what you're doing, and we'll compare and run sizing calculations, bearing calcs, moment calcs, thrust calculations, and figure out, is the actuator fully capable of what you're trying to do? And we know what specs will sort of be dependent at that point. All right, so talk through some product technologies here, what sort of goes into making an industrial actuator. Typically in industrial applications, you are going to see screw-based drivetrains and belt-based drivetrains. So we'll start off with screws. The simplest of this is a lead screw, right? Imagine you have a stationary nut, a nut that you are holding and preventing from rotating, and you spin a threaded screw, it's going to move the nut forward. Lead screws are incredibly cost effective, and trapezoidal type profiles can be self-locking. You can also tolerate a good bit of contamination. You don't have small precision rolling elements moving through there, but you do have some disadvantages being low speed, low duty cycle as well, because they are friction based, meaning they're also kind of inefficient. And being that they are friction based elements, as they wear, the backlash in that screw is going to change and your repeatability is going to open up a good bit. The drivetrain, the screw drivetrain that we use the most is called a ball screw. For those of you who aren't familiar, this is sort of the rolling element bearing of the linear drivetrain world. So we take a threaded screw and a nut filled with ball bearings, recirculating ball bearings, is placed on that screw. So the advantages there are you can get 100% duty cycle, 90% plus efficiency, way more precise than a lead screw. And they do come in varying accuracies as well. The way that thread form is cut can be typically rolled, machined cut, or ground. Ground screws are going to be your most accurate, and you can get those down on the micron level from a repeatability perspective, but they are quite costly. So typically we're not going to use them in industrial type units where that sort of precision is not necessary. The advantage with screws, any type of screw drive, is that it does add an inherent mechanical advantage for the motor, reducing your reflected torque and your reflected inertia. So something like a belt drive, for example, is not going to put any kind of mechanical advantage to the motor, so you may end up needing a gearbox to make that work. Screws are pretty speed limited though. There's a concept called critical shaft speed, or commonly referred to as screw whip. It's a function of really how long the screw is, the diameter of the screw, how heavy the screw is. Eventually you can start spinning that screw so fast that it'll start looking like a jump rope. And at that case, you end up putting some pretty extreme loads on the screw and end up causing a failure pretty quickly. So screw drives are typically more costly than belt drives, but they do have an inherent reduction, which means you generally aren't going to need a gearbox. So it can kind of sometimes be a wash cost-wise, depending on what you're trying to do. So belt drives, a very, very common industrial type drivetrain. So we use synchronous tooth belts, and these aren't the typical black rubber belts with Kevlar reinforcement that you'll see on something like a consumer grade 3D printer. These are polyurethane type belts with braided steel core. And because we use belts like that, sometimes people are always afraid of belts are going to break, things like that. We have never, in the 20 plus years we've been manufacturing belt drives, we have never had a belt break. So these things are great for long strokes. We make some actuators that'll go to 10 plus meters using belts, high speeds as well. They're pretty low cost for the kind of performance you can get out of them. And you can still get an incredible amount of thrust force out of belts like this. So disadvantage here though is there is no inherent mechanical advantage for the motor. So you will end up in a high load, high speed type situation. You may end up having to add a gearbox between your motor and your actuator to make this work. Excuse me. Belts are also very contamination resistant as well. We're not, again, talking about elements, rolling type elements that don't need lubrication, and if any kind of contamination gets in there, you could potentially have some problems. So we'll talk about some typical industrial guidance. This is not all inclusive of what kind of guidance elements you'll see in industrial applications. We're typically just talking about what kind of elements that we use. So the most simplest element would be like a Gibbs and Ways, like you'll see on the old Bridgeport type milling machines. We obviously don't use those in any kind of actuators here, but typical ones that we're going to use are glider bushings, which is really just as simple as it gets. It's a plain bearing that rides directly on some type of element, friction based. Roller wheels on some of our heavier duty type belt drives. And then the sort of Cadillac of the linear guidance world being the square rail bearing. So glider bushings are sort of the lowest performance and lowest cost type of guidance element we offer. Preload, any type of bearing needs some type of preload to make it work. Otherwise, you'll end up having a lot of play and the bearing really isn't doing its job. Preload is just accomplished by fitment between the element and the extrusion. There's a slight interference there where that glider bushing is going to be compressed. Bearings can ride on just raw anodized extrusion without any kind of secondary machining, really keeping the cost down, because really at that point the bearing is just an inexpensive piece of silicone impregnated plastic. These are low payload, low speed, also low stiffness and accuracy, but in these type of application where you're looking at a glider bushing, those aren't really specs that you're going to care about. So roller wheels, as I mentioned, all bearings do end up requiring some type of preload, and the way that's accomplished with roller wheels is with eccentric type loading. So 2 of the wheels on each side of that carriage will be preloaded upward, the other 2 will be preloaded downward. These are really nothing more than a radial type ball bearing with a plastic wheel on it. Pretty quiet operation. Also good for high speeds and for long strokes. We're not worrying about how long can we get a square rail manufactured and how long can we align that rail. Pretty good for moderate loads as well, but this is still an elastomeric element, so you do potentially have some stiffness concerns. And with any bearing, if you are susceptible to skidding if acceleration is too high, at which point you'll start wearing flats on your wheels and eventually start locking the actuator up. Great for contamination though. If you've got dust and debris getting inside of your actuator, typically, unless it's just some massive hunk, these wheels are going to roll right over it and not care. They do use shielded type bearings as well for that reason. So square rail bearings, these are by far the highest performance mechanical bearings that we offer. Typically, and not typically, but in a lot of times, they're going to be deployed in dual rail setups, meaning very high loading, very high moment loading. Accuracy and performance is really based on the mounting surface. So in a precision type application, you may go ahead and grind the base that you're mounting the rail to for some very good flatness. In industrial applications, we'll typically just machine it flat, which gets us really close enough and without adding too much cost. Nice thing about square rails, they do have the same capacity whether they are loaded in tension or compression. So very high stiffness as well. We're not talking, there's no elastomeric bearing elements in these things at all. Typically it's steel on steel rolling type contact, meaning very, very low friction and very high efficiency. Very high speed as well. These are, other than potentially roller wheels, these are kind of the fastest bearing that we offer, but we are limited on speed due to the return cages. So if you start moving too quickly, you'll see the black plastic portion on the back of that bearing. That's what allows the rolling elements inside to recirculate. If you start moving fast enough, the bearings will just end up shooting through that. But we're talking on in excess of 10 meters a second at that point. High loads as well. These will also skid if you're over accelerated, but again, we're talking upwards of 5 Gs. So let's get into our first product set. We're going to kind of go from with a good, better, best mentality, starting with what's our most cost-effective, lowest performance for applications that require that, and moving into some more premium type and higher performance type actuators after that. So the OSPE, it stands for Auriga Systems Plus Electric. If anyone's familiar with pneumatics, you're probably familiar with Auriga. They developed these actuators around the time that Parker acquired Auriga to be drop-in replacements with their pneumatic counterparts. So they're all designed around a ISO cylinder type bore, designed for modular flexibility as well. They're highly configurable, ordered down to the millimeter from a travel perspective, utilizing universal dovetail type mountings with a variety of available mounting options to suit your needs. Start off with the OSPE-B, which is a standard belt drive with glider bushings and by far our most price competitive actuator. Very low precision when you don't need any kind of precision, low to medium load, high, medium to high speeds, being that it is a belt. Holds up well in industrial environments too, just due to a glider bushing and an IP54 rating with that strip seal on top. Typically, these are going to be used for point-to-point type moves, nothing really precision. Example, we've got some machine tools in our shop that we actually manufacture these products on that use these as automated door opening type systems. These do typically excel in thrust only type applications. So wherever you would have typically used a rodless pneumatic cylinder, you can use one of these units, no problem. And also, as typical with rodless pneumatics, there are options for external bearings to be bolted on the side. These are user installable. They use a pretty interesting yoke type design. So we're not talking about having to precision align bearings to the drivetrain to prevent any kind of binding, really saving on cost as well. Pro lines and power slides are the two options we have. One is really optimized for high capacity and high speed. The other is designed for high capacity, lower speed, and more harsh type environments. These units are also available with a ball screw and trapezoidal screw. It's identical to the unit we just went through before, but with screw drivetrains instead of belt drivetrains. So SB stands for screw ball, basically ball screw. Medium speed, medium thrust, higher precision than a belt. Trapezoidal screw, this is really nothing more than the metric version of an Acme screw. Very low speed in this case, just due to the precision type nature. Higher thrust than the ball screw version though. And don't take that as a rule of thumb that trapezoidal screws are going to be higher thrust than ball screws. That's just kind of the way it works in this unit. Just due to the size, we're able to get a larger diameter lead screw than ball screw in these units. So let's talk for a second about vertical applications. So there's a lot of people that are afraid of putting belts in vertical applications because of that sort of belt break mentality. We put belts in vertical applications all the time. Again, I've said we've never had a belt break before, and some of our products specifically designed for vertical applications do use belts as the primary drivetrain. That being said, there is an inherent disadvantage to belt-driven and ball screw products in vertical, being that they are such high efficiency that they are back drivable, meaning in a power down situation where the motor loses all of its holding torque, the payload does have the potential to drop based on the lead of the drivetrain and what kind of inertia there might be in the system due to gearboxes. This is, in the days of modern servos, this is easily combated with fail-safe type holding brakes, but that does add some cost. In a lot of these OSPE type situations, these are very cost-sensitive applications. You may just be using a standard off-the-shelf type stepper motor or an off-the-shelf stepper drive that typically don't have the ability to use fail-safe type brakes, and even if they do, they're not going to be truly fail-safe due to just the fault type nature of those systems. So in that case, you might want to consider a trapezoidal screw, being that they are self-locking. Not all trapezoidal and Acme screws are self-locking, only certain leads are, but every lead that we utilize on the OSPE is a self-locking type system. Now, there are trade-offs in this case. You do give up precision and speed and duty cycle, but if you're in an application where you're trying to keep it low cost and don't have the ability to add any kind of a servo or a fail-safe holding brake, typically you're not really going to care too much about your precision. So this is the OSPE BHD, standing for belt heavy duty. It's a low profile belt drive with an internal square rail bearing. And this is by far our most popular out of the OSPE product line. I have this deployed in dozens and dozens of OEMs today that have sort of standardized around this product just due to its versatility, low profile, and performance. So I mentioned this uses square rail bearings, so much higher normal loading and moderate type moment loading. It is a single rail type setup, so not going to be as high of loading and moment loading as a dual rail setup will get you. Very good for high speed and high acceleration. It's going to be a little more precise than the OSPE-B as well. Also good for harsh environments because it does carry that same IP54 rating, and everything in the OSPE product line has a minimum of IP54. So the BHD it's a pretty simply designed product. You can see by the cutaway image we have there, it's really, you've got two pulleys, one of which is fixed, one of which is a moving pulley to apply tension to the belt, and designed around square rail type bearing. So there's really no kind of precision alignment needed. Everything is floated in just due to some of the way it's been designed and some of the machining processes we're utilizing. It does utilize dual trucks for higher loading, higher stiffness, and a little bit higher moment loading. Not as high as a high moment product with dual type rails. Very low profile as well. So typically, if you see the way that shaft is centered, the motor will either mount up or down, which is a pretty unique mounting type situation that allows this unit to be put into some pretty tight applications that have some pretty tight space constraints. It does utilize the same flexible mounting type features as the OSPE glider bushing variants. You have the dovetail grooves, or dovetail mounting on either side and on the bottom as well for side mounting, or if you just need to put the mount somewhere else due to a space constraint. And the end caps on these units are actually drilled and tapped as well for some type of end cap mounting, or if you were to put this into, say, a vertical application, mount the carriage, fix the carriage in place, and use this in a carriage to carriage moving beam type actuator, you could very easily mount end effectors and end of arm toolings on the end of the unit as well. The advantage to using square rails, and why a lot of OEMs will gravitate towards using this product, is because we can provide detailed life calculations for, we know how long the actuator is going to last, when you'll need to perform any kind of PM, and we can sort of assure people that we can hit their life requirement and their sort of machine life cycle that they and their customers are looking for. So this brings us to the highest performance industrial product that we offer. This is the high moment rodless, abbreviated HMR. This unit is available with both ball screw and belt drivetrains. It's sort of what we call a precision whirled ball screw, which gets you almost to the precision of a ground ball screw, but at the cost of a rolled ball screw. Rolled meaning we're just either heating the screw up and hot rolling threads into it, or cold rolling threads like you would make any other fastener. Whirled means you're basically machining the screw, or cutting it like you would a gear, meaning it's not as costly and long of a process as grinding, but it's a lot more precise than a process such as rolling. We use a high efficiency RPP belt for these actuators, for the belt drives, and it's an incredibly wide belt, meaning we can get a very high amount of thrust out of these units. It utilizes a small diameter pulley as well, meaning the mechanical disadvantage that the belt puts on the motor is minimized as much as possible, meaning you can typically get away with some lower gear ratios on this product. You don't have to start moving to two-stage planetary gearboxes that can add a good bit of cost. So for high moment loading, this is a dual square rail product, meaning there are 2 rails per actuator, each rail having 4 trucks. There's a bearing truck in each corner of that carriage. I mentioned this is a precision whirled screw, meaning we're about sub 1,000th or 20 micron of repeatability on these units, but this is still not what I would call a precision product. If you're caring about getting less than 20 microns repeatability, we do have products for that, but that's not necessarily what this product is intended for. This product is sort of the in-between of sort of lower precision or medium type precision applications. So I mentioned the RPP belt. That belt allows for smoother tracking and less cogging, so you'll get smoother motion at the carriage, also at higher efficiencies. Longer strokes than screw drives, but we still maintain the same form factor. They're both built on the same extrusion and use the same carriage, so the mounting of these 2 actuators is going to be identical, just with the exception that the belt drive is going to kick the motor out at 90 degrees, and the screw drive is going to have the motor out in line. So HMR, as the name implies, capable of high moment loading, using 1 actuator to accomplish what you might have needed 2 parallel axes for in the past. So we've done a good bit of market research on this product, and we can honestly say this is the most versatile and feature-rich high moment product on the market today. You know, not necessarily that it has that many unique features that competitors don't offer, but this is probably the only product that offers all of those features in one product line. So meaning you're potentially able to standardize on one type of actuator, meaning it's knowing it's going to fit basically every application you can throw at it without having to be up to speed on multiple different product lines. So some design features. This unit is available in 5 frame sizes, from 85 millimeters wide up to 240 millimeters wide. So why do we offer so many frame sizes? What this means is we can be right-sized more often than a lot of competitors can that may just offer 3 frame sizes, meaning you're not necessarily having to pay for additional bearing capacity that you don't necessarily need because the smaller size isn't going to do what you need it to do. So we also have 2 profile options. You can see that on the right there, those cross-sectional views of the extrusion. We call one of them the standard profile, and one of them is the reinforced profile. So you have the option to add rigidity to the actuator if you need it to be self-supporting. So the disadvantage I mentioned with rigid actuators is typically some higher cost, just there's more aluminum there. It's going to be more costly. It's going to weigh more because, again, more material and a larger footprint. But with this product, you can choose whether you need that or not, and that's sort of with the mentality of pay for what you need and none of what you don't. 2 screw leads per frame size. So again, why do we offer 2 different leads? Really, it comes down to speed and stroke. So the critical shaft speed of a screw is a constant value depending if I have 2 screws with different leads that are the same length and the same diameter, they're going to have the same critical shaft speed, measured in revolutions per second. But if I change the lead of that screw to make it a faster lead, so 25 millimeters per rev as opposed to 5 millimeters per rev, you're able to get a higher linear speed out of that screw. Now, the coarser lead, meaning the faster linear speed type screw you go, you do start giving up some of your mechanical advantage. So your trade-off here is that you potentially increase your motor torque. A big advantage to the HMRB is the motor mounting orientation. So you can see by that image, you can choose anywhere in 90-degree increments, 360 degrees around that actuator to place that motor. So if you have a height constraint at the end, put the motor out to the side. If you have a width constraint, you can put the motor up or down. And the motor, the 270 and 90 options where the motors come out to the side, those are actually field changeable. So the actuator will come with universal end blocks that have provisions for moving your motor mount and coupling housing to either side of the actuator, being the drive side, the side you got it on. You can move it down to the complete other end of the actuator if you so choose. The reason we're able to do that is because the HMRB actually tensions at the carriage, the belt tension. Another advantage there is you can actually change your belt should you need to, or adjust your tension without having to remove your payload, meaning you're able to minimize your downtime quite a bit. Now, cover options. So we saw, let's go back to the last slide for a second. You see that those 2 cutaways there, you can see the drivetrain on one end, but you can't on the other. That is due to the optional IP54 cover that you can add to the unit. With that same mentality, if you are in a clean application where IP20 is going to be enough for you, then you won't be stuck paying for all that additional IP54 rating if you don't need it. So again, can be ordered with or without strip seals, and strip seals are it's an industry standard sealing type element, but they are wear items, right? There's end caps, wipers, and seals that will wear out over time and would periodically need to be replaced over the years. So if you don't need IP54 protection, I would definitely recommend going without it. Just you're minimizing your product life cycle cost, basically. So everything I've presented so far is out of what we would call our standard product portfolio, which is really what we call industry leading products with competitive lead times. Lead time on these products can be in the 1 to 3 week range, depending on what kind of options you need and what your volumes are. We also have considerable customization capabilities, and most of what we do are simple modifications. So if you have an additional third-party motor that you'd like to utilize, we do custom motor mounts every day, custom travels, adding custom options, such as a lot of people these days are wanting payload mounted feedback for their servo system, so a linear encoder. We put linear encoders on HMRs all the time. Those are what we would sort of call simple modifications. Purge ports for dirty type environments, multi-axis systems. If you need to put together a 3-axis type system, we have standard mounting brackets for that, and they can be assembled and factory aligned by us. We also go up as high as to go with ground up systems for OEMs. Oops, sorry. So we sort of posture ourselves based on selectable levels of risk reduction. So I mentioned our standard solution. These are pre-engineered products out of a catalog, highly configurable though. So as I mentioned, you're able to order these with a variety of options. If, for example, our product, the 404XR, which has been, it's a precision screw drive product that we've been manufacturing for 20 plus years. There are, I believe, over 1 million possible combinations of standard options that you can order that are catalog type options that are rapid deliveries in the 5 days to 4 week type range. We also offer modified solutions, so engineering value add, bundled subsystems. So, if we're putting together a multi-axis system, we're able to put all of those units together with all the kind of mounting brackets, any kind of motors and controls as well. We're able to do those in the 3 to 6 weeks type range, and we go as far as to go with complete custom solutions, so engineered to OEM specifications utilizing a stage gate process I'll talk about in a second here that's fully synchronized with the OEM. So this stage gate management, this process is actually overseen by our engineering manager, who is actually a Six Sigma design black belt, has been doing this for 20 plus years. So obviously starting at an idea generation phase where someone like Paul might come to us and say, hey, here, I have this OEM where the standard product isn't going to work for whatever reason. We'll sort of identify the need, figure out what the specifications are going to need to be, do a feasibility review to see, all right, can we do what is being asked of us, and can we do it inside the price and delivery type time frame that are being asking for. If that ends up being a yes, then we'll go to development qualification and pre-production, where we'll work on product definition, again, direct engineer to engineer contact with OEMs, put together specifications, go through design FMEAs, again, fully synchronized with the launch schedule of the OEM's product, all the way through qualification and results, manufacturing plans, custom test stands as well. We'll do custom acceptance testing for OEM products. We'll even go as far, if we have a large enough opportunity, we have implicated dedicated manufacturing cells based on people's forecasts and what their needs are. So I know that's a lot of information to throw at people very quickly, but we're kind of drinking from a fire hose. So if there's any questions, Paul?
Yeah, great. Thank you, Adam. We did have a couple of questions come in via chat while you were going on, so I will read those out to you right now. First question that came in is, what does RPP stand for when you were talking about the high efficiency belt on the MR?
What it stands for off the top of my head, I don't remember, but it is basically, typically a belt is going to be a trapezoidal type tooth. We've used those before, like an HTD type profile. What these actually are rounded type profiles, so you don't get the impact of a squared off tooth section hitting the pulley, which you'll actually, if you're monitoring close enough from a linear perspective, you will see that and you'll feel it moving forward. You can see it in your process. That's minimized with the RPP. It's also a higher pitch belt, so you're going to have more in the same linear distance, say 5 inches, you will have more belt teeth in 5 inches than you will on a more trapezoidal type belt. So you're not going to see those impacts as much, and you're able to get a little more granular, a little finer resolution from a motion perspective.
Okay, thank you for that. Next question that came in, where are these products that you covered manufactured?
They are all manufactured in the US, but they're not limited to US manufacturing. Everything I've mentioned today is what Parker calls a global product. We have multiple manufacturing centers throughout the world, all manufacturing basically the same product. Now, we all operate autonomously, so it's not like if we need to do some kind of modification, I need to work with the engineers in the plant that quote unquote design the product. All of our manufacturing centers are also design centers. But these, for example, the OSPEs are manufactured in the US in Irwin, Pennsylvania, right outside of Pittsburgh, and we do stock everything we need for rapid delivery there. They're also manufactured in Germany and Korea as well.
Okay, thank you for that. Another question that came in, what if I need a product with incredibly long travel, say maybe over 10 meters, and high rigidity to mount in a self-supporting fashion?
Sure, yeah. So the products I mentioned today will go up to about 5,400 millimeters of travel, which is in a good 80% type use case. We have an additional product that we just kind of don't really necessarily have time to go through today, called the HPLA. It's a roller wheel type unit that rides on extrusion, and that unit will go upwards of 20 meters of travel. It's very rigid type profile, square profile. For example, the middle size of the HPLA is what we call the HPLA 120, which is 120 millimeters square type profile that's incredibly rigid. We can go, multi-meter unsupported span with those units. But they're very rigid, which makes them heavy. Not the most size constraint friendly type product, but it is an option should you need it.
Okay, and then another question that just popped up. I think you've covered this. The typical lead time, if I heard you right, it's 1 to 3 weeks for standard product for the most part. Is that accurate?
Yep. Yeah, that's accurate, depending on what you're doing. There are some options that can be a little bit higher lead time, and once we start modifying products, if it's something more than just a custom motor mount, something like that, you could potentially be looking at some higher lead time, one, just for the design time, and two, for actually sourcing the components necessary. But we target the probably 4 to 6 weeks on modified product.
Great, thank you. Any other further questions? You can add those in the chat. All right. I don't see any coming in. So again, I wanted to thank everybody for taking the time today, and especially thank you for Adam and your time and sharing the material. One of the things that you mentioned is the Parker Virtual Engineer, and just wanted to remind everybody in the materials section of the control panel, there is a brochure on that Parker Virtual Engineer, and we'd love to show you how to use that for sizing in the future if you have an application or an opportunity that you'd like us to look at. It is a web-based sizing tool. Oh, looks like he just kind of popped into that. Thank you, Adam. He's kind of showing it right now where it is a web-based sizing tool, and that brochure will have the web link for you to go out to the parker.com site and find that sizing tool, which again, you can certainly take it on yourselves, or we've got the team here to help you with that as well. And with that, again, thank you everybody for your time today, and thanks again, Adam, for the presentation, and we look forward to everybody on a future Kundinger Presents.
Absolutely. Thank you. Thanks for having me, Paul.